Welcome everybody. My name is Ergin Kulenovic. I have been working for Alfa Laval for the past 6 years, and I currently hold the position of a sales development manager, working tightly with the regional business managers within process parts and service. Today we will be talking about total cost of ownership for plate heat exchangers. I will do this by bringing up 2 customer cases. The first case is about a customer within a process application. The customer uses pond effluent water to cool its own process water. The setup of the heat exchangers is 9 identical MX25B plate heat exchangers with 300 plates. They are connected in parallel, and on top of this the customer has 1 extra heat exchanger which is used while one of the other 9 is cleaned. These are fairly big heat exchangers, about 2.5 meters height and 1.5 meters width. So cleaning them is a bit of a challenge. The pond water side needs frequent cleaning, and the method used by the customer was manual cleaning, meaning that they opened each heat exchanger when needed and they cleaned every plate by plate. One of these cleanings took approximately 4 days. The complete cycle was done in 6 weeks, meaning that they took down 1 heat exchanger, cleaned it, closed it back up, opened another one, and so on. They did all of this in sequence. This was more or less continuous work for 2 men. And another side effect, apart from this being a time-consuming and a difficult job, was that the gasket lifetime was reduced to 4 years, out of perhaps 8 that it should have lasted, or 10 maybe even. There were some deformations on plates and gaskets crushing as a result of frequent opening as well. As you may know, every time you open a heat exchanger, there is a risk of something happening while closing it again. In order to help the customer optimize the maintenance process, Alfa Laval did a heat exchanger audit. We did individual alpha check measurements, which is a performance measurement done on a heat exchanger still running, to see how fouled it is and to see whether or not it needs to be cleaned. The proposition was to do CIP, the chemical cleaning of the heat exchangers, instead of manual openings when possible. This is much less time consuming and cheaper. Also, it does not involve as many people in the maintenance procedure. The openings of the heat exchangers, if possible, will be done only when absolutely necessary. Not every time, but maybe every 3rd or 4th time if possible. The actions that this resulted in was that we saw that not all the PHEs need to be cleaned every time. Some of them got dirtier quicker than others, and this depends on the distribution in the piping. On average, the CIP needed to be done every 5 weeks, but the gasket lifetime increased to 8 years. As I mentioned before, AlphaCheck is a service that lets us check the performance of the heat exchanger without opening it. Each of the boxes represents a percentage of the performance of that heat exchanger at that time of measurement. Looking at the first column, we can see that not all heat exchangers were as badly fouled. For example, number 2, number 5 and number 10 are in pretty good shape, and they do not need to be cleaned right now. The green light represents a heat exchanger in a good state, yellow in a state where we need to prepare for service, and red in a badly fouled state where we need to clean it. Based on this measurement, we decided which ones needed to be cleaned. For example, number E111, E113, E116, and so on. At the next measurement date, we measured all of the heat exchangers again to see which of the ones have progressed from green to yellow or to red, or from yellow to red, and to know which ones to clean then. We could also see what happened to the heat exchangers that we cleaned the last time. In this case, for example, number E111, it had gone from 60 to 98%, meaning that it was cleaned well, and then it started to deteriorate a little bit, but it's only a couple of percentage. What we can also see with the trend when we do this several times is that not all heat exchangers foul as quickly. Looking at, for example, the bottom two rows, number 119 went from being cleaned at the second date measurement at 99%. Within a little bit more than a month, it went down from 99 to 72%. Whereas looking at the one below it, in 2 months, it went from 98, looking at the first column, to 85 in the last column, so only 15%. This gives us an indication on which positions are more subjected to fouling and need to be cleaned more often. So, what does this mean for the customer? The calculations done here are based on the cost of doing manual cleaning, i.e. labor, time of that, the reconditioning, i.e. refurbishment of the plates involving change of gaskets every 4 years before the optimization and every 8 years after the optimization, the cost of performing the alpha check service, and also the chemical cleaning, the usage of chemicals, the equipment cost and the labor cost involved in there. Before the optimization of the maintenance procedure, the customer was looking at a yearly spendings of around 330,000 euro. Remember, this involves a portion of the gaskets being changed every 4 years. After the optimization, instead of changing gaskets every 4 years, we're now changing them every 8 years, which means there's half as much cost in that. The manual cleaning went down significantly to about a fifth of what it was before, and those are the savings made. Of course, there is an added cost of the CIP and also alpha check, but looking at the total cost, you can see that the cost has decreased from around 330,000 euros down to about 170,000 euros a year. In conclusion, introducing predictive maintenance and optimizing the maintenance process lowered the maintenance cost by 170,000 euros a year, meaning about half of what the customer was spending before. Not only this, but this procedure safeguarded uptime. There's much more control of what needs to be done and when it needs to be done than before. And also, by keeping the heat exchangers at a higher level by doing maintenance in time, not at a preset schedule, but when it's actually needed and in the way it's actually needed, gives a higher average thermal performance and more yield out of the heat exchangers. This means that the heat exchangers can actually do what they're supposed to do and be utilized to their full potential. The second case is within a process application where the customer uses seawater to cool an internal cooling loop that cools the rest of the factory. This is usually done when seawater is being used for cooling, so that you can isolate the contact of the seawater with a piping by just allowing it to come in contact with a set of heat exchangers, and then the rest of the piping can be done in stainless steel. For this matter, in order for the plates not to corrode, the heat exchanger plates are most often done in titanium. In this case, the customer has 8 M30 PHEs, again a big size of heat exchangers, with 500 titanium plates each. The customer used CIP, cleaning in place, the chemical cleaning. The frequency was once or twice a year and was based on experience. In the summer, the cooling needs are often the biggest, so the customer cleaned in the spring. The maintenance procedure used by the customer did provide an immediate improvement to the performance of the heat exchangers, but did not always last as long as it should have. The results of cleaning were irregular due to the fact that the customer did not know how well the heat exchanger was cleaned, since it wasn't opened, and this resulted into lack of cooling capacity from time to time. There were major disturbances in the process, as this is a vital part of the customer process, and sporadic loss of production. If the customer cannot cool the product enough, he has to reduce the production. Looking at a yearly perspective, this meant a total average loss of about 10% of production for about duration of 3 to 4 days. And this cost about 200,000 euros per day in production loss. A significant. Again, in order to assess the situation fairly, we proposed a heat exchanger audit. We did individual alpha check measurements on each and every heat exchanger before and after the chemical cleaning. This was done in order to assess and quantify the actual result of the cleaning. When you do CIP, you do not open the heat exchanger, and this sometimes means that you cannot confirm how well the heat exchanger has been cleaned without doing the alpha check measurement. Using this, we could establish a frequency for the CIP cleanings. How often do they actually need to be cleaned in order to keep the heat exchangers at optimal performance? The actions taken based on this are regular alpha check measurements twice a year on each of the heat exchangers. Now, you can argue that once you do a couple of performance measurements on the heat exchangers, you would know how quickly it gets fouled up, and you can clean it when needed or in time. The fact is that the process conditions change all the time. It can be everything from the process flow increasing or decreasing. It can be from the quality of the product changing. It can be the temperature of the cooling water going up or down, seasonal changes or yearly changes. This means that you need to check the performance regularly, even though you think that you know when to clean. We also discovered that the CIP frequency needs to be increased to 3 to 4 times per year. As I mentioned before, if the heat exchanger is badly fouled or even has clogged channels, then the chemicals cannot enter those channels or do not have sufficient time to work in the heat exchangers, meaning that the plate will not get cleaned. The channel will not get cleaned, the plate, some sections of the plate might not get cleaned well enough. But if you do CIP in time, where the fouling is not too severe, then the chemicals can work efficiently, and this is a very time efficient and cost efficient process for cleaning the heat exchangers. The most important thing for the customer is that this new procedure meant a more stable production, and the customer could go from a 3 to 4 days average loss to only 1 day average loss. Looking at the financial implications of the customer's procedure before and after, you can see that before, the biggest portion of the costs was not related to maintenance directly, but was related to the indirect cost of losing production, about 700,000 euros per year. The customer already used CIP, but that is in comparison, an insignificant part of the cost. After the change of the maintenance procedure, there was an added cost of the CIP cleaning, which was actually doubled. And of course, there is a cost of doing the alpha check measurements and evaluations of the report. On the other hand, the customer reduced the indirect costs by 2.5 days of production loss, by almost 500,000 euro. In conclusion, introducing predictive maintenance and optimizing the maintenance procedure resulted in higher maintenance cost by 30,000 euros a year. But on the other hand, it lowered the production losses, the indirect costs, by 500,000 euros per year. This, of course, is a significant savings for the customer that is seen straight away with no payback time. But also it gave the customer the peace of mind, knowing that the production is secure and there are no unexpected surprises. If you would like to know more about these cases or any other cases, or you just have any questions about predictive maintenance, parts and service in general, or heat exchangers in general, please visit Alfa Laval at www.alfalaval.com or contact me directly at my email ergin.kulenovic@alfalaval.com or give me a call at the phone stated here. Thank you very much.